So, for the remaining 3 lectures, I will be talking about joint work with Baptiste, and in fact some work that he did by himself. So the topic is now slightly shifted to zeta functions from motivic L functions. So just to recall what I said before, motivic L functions are important if you want to prove things, if you want to relate things to automorphic forms. But zeta functions are conceptually much simpler. So again, they're given by this Euler product, as was mentioned before, and all you can say is that it will converge in some right half plane bigger than the dimension. So if I forget to mention any assumptions, my X will always be what's written here, a regular connected scheme of dimension D proper over spec Z, but it could be a variety over a finite field. So that's covered by this discussion, whereas it wasn't covered by motivic L function. Of course, the aim is, again, as before, to describe these 2 quantities, the vanishing order as a moromorphic function, which is an integer, and the leading Taylor coefficient, which is a real number. So, so the precursor to our work was ideas of Lichtenbaum. So let me just recall that this whole idea of motivic cohomology also was very much proposed, or I don't know if it was really invented by him, but certainly since the mid-70s, Lichtenbaum was advocating this idea of motivic cohomology, and he was motivated by special value conjectures throughout, and he also came up with this idea of the Weil-etale cohomology. So there's 2 key ideas in this subject due to Lichtenbaum. So what is going on? So we're in the case of a variety over a finite field, smooth proper. We want to describe these special values in terms of motivic cohomology. So at S equal n, we have the motivic complex Zn. And here, because you're over a field, you could take either higher char or Suslin-Wolwatsky complex. As Lars suggested to me before the conference, we want to avoid algebraic cycles in this conference. And I think there is a way to do that. So you have to take, you could take neither of them. You could take motivic graded pieces on Selma-K theory, and I think you would also be good for this discussion. But let's just stick with the classical setup. So you have some complex, and in low weight, these are very concrete. They're quasi-isomorphic to Z or GM. And if you're interested in L values, you always have to take motivic cohomology in the etale topology. Otherwise, you don't get correct things, at least in the etale topology, but it has to be modified, which is this Weil-etale idea. So what is the Weil group? So this is just the copy of Z spanned by the Frobenius inside the Galois group, which is a Z hat. So that's something everybody's learned in basic algebra. And if we just take our X to be spec Fp, so it has dimension 0, and we take n equals 0, which is the only point where there is a rank of the zeta function. So recall the zeta function for spec Fp is just a single Euler factor. It looks like that. And it only vanishes at S equals 0. So the vanishing order is 1 at 0, a polar order, in fact. And so if you look at the Galois cohomology of the motivic complex, which is just Z in this case, you find this. It's a Z in degree 0 and Q mod Z in degree 2. Again, the computation many people have seen. Whereas if you take the Weil group, you get Z in degrees 0 and 1. The H1 is just Homs from Z to Z, so you get another Z. And so that's kind of the origin of this idea of Weil-etale cohomology. We turn these co-finitely generated groups, Q mod Z, into finitely generated groups in a previous degree, the Z in degree 1, by this idea of replacing the Galois group by the Weil group. And this works in general. So if you now just take, for example, a curve at n equal 1, the etale cohomology of GM looks like this. Of course, you get the units. You get the Picard group, which in this case is finite plus Z, given by the degree map, right? So you can imagine the Picard group being given by char 1 divisors modulo rational modulo linear equivalence because X is regular. And then you have a degree map on divisors, which is this Z. And if you compute the Galois cohomology further, you again get this picture that you have 0 in the next degree and then a Q mod Z in degree 4 in this case. And if you took Weil-etale cohomology, then you get 2 copies of Z instead of this Q mod Z. And this Z remains. So in other words, you turn the etale hypercohomology of the motivic complex into a perfect complex of abelian groups. And the analytic completion doesn't change, right? If you analytically complete this complex, you again get a ZL in degree 0 and 1, and the same for this. So it's kind of a modification of the rational homotopy type of motivic cohomology without changing the analytic homotopy type of these complexes for any prime L. Okay, so in general, if you have a smooth proper X, you define its Weil-etale cohomology just by descent from X extended to FP bar under the Weil group rather than the Galois group. So if you put the Galois group, you get ordinary etale cohomology. If you put the Weil group, you get conjecturally perfect complexes. But of course, if you have any examples that are beyond these cases here, you unfortunately don't know finite generation. So the general expectation would be that these etale motivic cohomology groups are finitely generated up to degree 2d plus 1, which would be this 0 here. Sorry, 2n plus 1 if you have twist n here. So they're finitely generated in low degrees, and then in higher degrees they become co-finitely generated. That's one of the big expectations, and we only know it in these low cases, this finite generation. But once you have perfectness, you have finite generation, so you get this Weil-etale complex, which is a perfect complex of abelian groups. And then you can describe the L values in a very appealing way. This goes back to Milne in the 1980s and then was worked out by Lichtenbaum-Geisler for the Weil-etale picture. So first of all, you have this long exact sequence after you tensor with R, where this theta is a class in H1, right? So we already mentioned there's a canonical class in H1 sending the Frobenius to 1. That's the class theta, the generator of the Z here in degree 1. And so the cup product with Zeta, with this theta, trivializes the real or even rational Weil-etale cohomology. So rationally what happens after you tensor with R, you get 2 identical groups in 2 consecutive degrees, and they can be identified with this cup product with the H1 class. So here you have the 2 Z's in consecutive degrees and so on. And in general, if you have a smooth proper variety and any n, you have 2 Chow groups in consecutive degrees. So the rank is much more mysterious than in these 2 examples here. This is the top degree where you just have a single copy of Z. This is the bottom degree where you also have a single copy of Z. But in between, if n ranges somewhere between 0 and the dimension of X, you have these mysterious ranks of the Chow groups, which are kind of random of arithmetic nature. And so these would be the ranks of these 2 groups in degree 2n and 2n plus 1. 3 terms? Oh. Why 3? Oh, you mean a triangle? Yeah, that's not what this is. No. Yeah, I take the actual cohomologies of my complex, and I have this map cup theta. So the theta is very special to the situation. It's the H1 class in, yeah. In fact, in this case, in general, it would square to 0, but again, since we only have 2 non-zero degrees, it's an isomorphism between those 2 groups. Yeah, and in fact, that's why I was switching back. I mean, you can see it concretely happening here. You have 2 identical rank groups in consecutive degrees. And what I was trying to say before is that the rank is much more mysterious for an n bit that's strictly between 0 and d. Yeah, then it's kind of arithmetic nature. Like if you take the Chow1 of a surface, like people have looked at many K3 example, whatever. It's always a mysterious rank divisors on a surface, for example. Whereas in the top degree 0 and D, it's just copies of Z. Yeah? Theta is the class in H1. Remember, H1 is Hom of the Weil group to Z. So sending the Frobenius to 1 gives you a canonical class in this H1. Okay. Yeah. So oh, the theta from the other lecture. Did we have a theta already? Oh, the B. Yeah. From an S1 action. Well, yeah. Okay. Yeah. I mean, this has degree 1, so it increases the HI by 1 if you take coproduct. And okay, and then the vanishing order of the zeta function is given by this secondary Euler characteristic. So once the primary Euler characteristic is 0, which follows from this exactness here, right? I mean, if you have a complex and you find some maps, between them that make this exact, so the Euler characteristic has to be 0, which it visibly is, because you have the same rank in 2 consecutive degrees. And then the secondary Euler characteristic picks up the actual rank of these groups. And this is the vanishing order, the zeta function. So, I mean, you verify it in these 2 examples I had at the beginning right away. And then the leading Taylor coefficient is given by, well, now imagine in all of these real spaces you have Z lattices, just given by the integral motivic cohomology, which was finitely generated in all degrees by our big assumption. And so you can actually sort of, in the determinant of this complex here, which is canonically trivialized by this cup theta map, if you take the integral sublattice, you get a number again, just like in the previous discussion. So the determinant of this integral sublattice gives you a number in R. And that's what I mean by this chi cup theta. And so this real number is almost the zeta value, except for this power of p. So this power of p was found experimentally by Milne in the 1980s, and it's given by this combination of Hodge numbers. So this is just the usual Kähler differentials on X. So the Hodge numbers of the smooth projective varieties. And it didn't have an interpretation as an Euler characteristic in any sense before Baptiste, like maybe 10 years ago, he discovered it's actually the Euler characteristic of Deram cohomology mod Fn. Yeah, so it's the weight n graded piece on cyclic cohomology of X. Yeah. Yeah. So I have an I here, and these groups are only non-zero if I is 2n, and then there's another non-zero group in degree 2n plus 1. Yes, it's just an isomorphism between 2 groups. I mean, you see it in this example, right? If you tensor with R, you just have these 2 in degree 2 and 3, right? That's what happens. Or here, you have 2 groups in degree 0 and 1. So the Euler characteristic of motivic cohomology does not give you the L value. Instead, you have this correction factor, which now we can understand as motivic weight n-graded piece on cyclic cohomology or on TC plus on the topological analog. And I was about to write that on the board, but maybe I do it tomorrow. From this prismatic, I mean, the zeta function. Okay, so let's say that later. It's actually very easy to see why this power of p appears together with the Euler characteristic. This is somehow the part that's coming from TC, and that's the part that's coming from TC plus. And if you express the zeta function as a characteristic polynomial on TP, which is crystalline cohomology, then you see these terms appearing right away. And maybe I should really sketch that on the board. I don't have it in my slides. Maybe I'll do it tomorrow. Yeah. Oh, okay, again. So you have this real complex which is trivialized on the level of determinants because of this exact sequence. So its determinant is isomorphic to R canonically. So the integral subdeterminant then gives you a real number. So that's the pattern by which we want to describe L values in general. So, yeah. The torsion, yes, together with the regulator, if you like, on these two pieces that have a rank. I mean, you have to identify these Z's with a cup theta map tensor with R. Over that exterior algebra, well, probably not, but no, I can't say anything about that. I mean, maybe you can interpret the cup theta map as a module structure over something, but I'm not sure you can interpret this as taking determinants over this ring. Oh, maybe we'll talk about that afterwards. So out of my head, I would say no, but maybe there is a way to do it. And yeah, if I put 0 here, I get when I is 0, well, I have H0 Z1, that's always 0. Because the Z1 is GM minus 1, so it starts with the H1, which is the units, right? H1 Z1 is the units. So this is just a finite, I mean, this is just the constant field units, because everything's proper. And so, and if I would take another D that's bigger than 1 for a curve, I would get finite groups everywhere. So the rank only happens for n between 0 and D. But this description is true for all n. So here I have no restriction on n. Any n in Z, even negative n. Same pattern, so it all works. And this is only there for positive n, this p power. Okay, so how do you prove such a thing? Well, let me just remind everyone that the zeta function is, thanks to Grothendieck's and Dwork's work and so on, it's very explicitly known. It's actually a rational function in the variable p to the minus s, right? So, and it's given by the characteristic polynomial of Frobenius on the geometric L-adic cohomology. And so you can kind of roughly imagine, if you want to describe the value of such a function, you have to derive with respect to the Frobenius action on the geometric theory. So you get the absolute theory, you get the L-adic theory of x itself rather than xf p bar. So the values are related to the Galois cohomology of geometric cohomology, which is absolute-etale cohomology, but L-adically we can also write it as Weil-etale cohomology. So and so the reason is that after L-adic completion, you can relate this to the motivic complex. This is again by this basic property. If you have a motivic complex in the etale topology and L is invertible, then it's just a very simple root of unity sheaf. And so this Tate twist just changes the Galois action on these complexes here. So so it's almost immediately clear from this formula that you get some L-adic Euler characteristic of this complex as a value of this zeta function. For the p-adic case, if L is equal to p, it's not so immediate. And that's what I wanted to write on the board, because using this prismatic groups, it's really quickly explainable. So this HI Chris is also prismatic cohomology in this case, or the weight graded piece on TP. And if you want to compute the value of this at some integer p to the minus n, then you see these two pieces coming in. So one piece is motivic cohomology, which is related to TC, and the other piece is TC plus, which gives you this factor. Okay. Now we want to move on to characteristic zero arithmetic schemes, unless there is still questions on this picture. Oh, yeah. I could also put a. I mean, this has two Frobenius. This has one on the on the FP bar and one on X, right? If you take the product of both, you have trivial action. It's a general property on etale cohomology. And so the Frobenius on X acts the same as the Frobenius inverse in the Galois group. And by convention, you take this Frobenius inverse in the Galois group. We could have written that Frobenius on X, and that's why you have the Frobenius here. Yeah, yeah. So, how does all of this generalize to characteristic zero arithmetic schemes? So I told you here you could take either the Haya-Chow or Suslin-Wojewodsky motivic complex, which if you write them down, the definition looks actually quite different, but there's a theorem of Wojewodsky saying that they're quasi-isomorphic. And in characteristic zero, we have to take the Haya-Chow complex, unless we believe in Selmer K theory with a motivic filtration. I think that's another alternative. And so let me just briefly run through that. It's really a construction that's of homological nature, that belongs to K prime theory, to coherent sheaves. And so you have this construction. You have an algebraic M simplex, which you write as this to have the coordinates having a simplicial structure. And then you just take algebraic cycles on this scheme. So you have a scheme Y, and you cross it with this algebraic M simplex, and you get, you take all algebraic cycles which intersect the faces properly, so you have a boundary map on these cycles. So that was Bloch's original idea for Haya-Chow groups. If you take cycles in the top degree, so in other words, where this M is 0, then you get the usual Chow groups. So you just have cycles on Y itself if I is 0. And the relations coming from Y cross delta 1 just give you rational equivalence. So so that was Bloch's big insight, that you can generalize the traditional Chow groups, which go back to the 1950s and so on, by this very kind of natural simplicial object to higher Chow groups. And yeah, so they're bigraded. And if you look at the definition, all the terms, these ZNs are actually etale sheaves, so you can view this Zn also as a cohomological complex by some reindexing, which I'm indicating here, in the etale topology on any scheme, basically. But one only does it for regular Y, because this reindexing is really is only sort of natural for regular Y, where you expect some kind of Poincare duality identifying homology with cohomology. Exactly, no. It doesn't. It wouldn't see nilpotence in the structure sheaf on the scheme. It just sees the underlying space of the scheme. But it does have this remarkable property in the etale topology, and L invertible on Y. It's just this very simple. I mean, this is hugely complicated, and so it just turns out that this is concentrated in degree 0 and just given by the root of unity sheaf. So all mod L to the n, all higher groups vanish in the etale topology if you sheafify. And then rationally it gives you the Adams eigenspaces on K theory. So this would follow from rational degeneration of the motivic spectral sequence, but I think Bloch already proved it directly in his original paper. He found maps back and forth between them, even before people knew the spectral sequence. So rationally, the Chow groups give you Adams eigenspaces on K theory, which is, if you recall from my last talk, these were the motivic cohomology groups appearing in my special value conjectures. So I might as well rewrite them in terms of higher Chow groups. Okay, The other key ingredient that doesn't appear at all in characteristic P is the lean cohomology, which is somehow the motivic cohomology from the Archimedean fibers. So again, I have my X of dimension D, and then the space of complex points is a complex manifold with Galois, with complex conjugation action. And you just take this Deligne complex as a sheaf in the analytic topology and take its hypercohomology, and that's its GAR equivariant cohomology, and that's Deligne cohomology. And you do the same with real coefficients, replacing Z by R here. So this is just a constant sheaf Z on this manifold, so it would give you the singular cohomology if this part wasn't there. And this part, if you're familiar with cyclic homology, it just gives you the weight n-graded piece on cyclic homology, the motivic weight n-graded piece. It's just truncated de Rham. This one. So this starts in degree 1, this is degree 0. Yeah. Well, the 2 pi I is how the Z is embedded into O. Remember, O is the structure sheaf of a complex manifold. So it has the complex numbers in it, and you send Z to 2 pi I n Z in the complex numbers. Because cyclic classes naturally lie in this twist. It has to do with the Betti-de Rham comparison isomorphism, which, if you take twist, changes by this factor. I think. Whereas the groups don't change under Tate twist, right? But the Betti-de Rham comparison isomorphism will change. Yeah, so this comes a little bit out of the blue. I don't know exactly why Deligne invented it. I think it's because there is a cyclic class map into Deligne cohomology which refines the cyclic class map into the ordinary singular cohomology, and because it introduces these Hodge conditions, right? So it automatically lies in the mod fill n part, and that's why you put in this truncated de Rham complex. But you can also view it as some kind of completed K theory. It would really be nice if this could be made rigorous using maybe condensed mathematics or something like that. Yeah, just this part, this truncated de Rham part, yeah. That's a standard computation. If you look in Laudet's book on cyclic homology, the weight n-graded piece is just truncated de Rham. And this is some kind of tangent space, right? If you take n equals 1, then all you have here is O, and this little complex here is just giving you the exponential map on the multiplicative group, right? This O is the additive group, and its relation to motivic homology in weight 1, which is units, is just given by the exponential map. So this part is some kind of tangent space to the motivic homology. Exactly, yeah. If you put all weights together, you can fabricate some Deligne K theory, which has this form. It's this pullback. Yeah, so this part would come from topological K theory, and then you have some fiber with HP and HN. And this picture would work again for any n, including negative n. So for negative n, we don't have a tangent space. But for L values, we want all n, including negative n. Okay. So these are my two ingredients, and now what replaces Weil-etale groups in characteristic 0 is something we call Weil-Arakelov groups. We thought they deserve a new name because, first of all, Arakelov groups will appear. Literally, the classical Arakelov groups will appear in this picture. Then they won't be perfect complexes. Remember, one of the key ideas of Weil-etale over finite fields was that we turn motivic homology into perfect complexes. They're not always perfect complexes. I'll tell you in a second what they are. And then also Lichtenbaum had this idea that the Weil-etale topology is somehow a refinement of the Etale topology. Yeah, so you can by adding objects which are not schemes, like this strange cover with group Z that that he adds in a scheme over FP, you can make some Grothendieck topology which is finer than the etale topology, and that was his original vague idea what this should be, but we don't believe in this idea anymore, so we should call this something else. There is no Weil-etale topology probably. So we have a new set of groups that we call Weil-Arakelov cohomology, which generalize these Weil-etale groups here over a finite field, and we construct them in a rather roundabout way. We start with the etale hypercohomology of Zn on our scheme X, again with these standard assumptions. And then we modify this. And I keep the modification under the rug, what we actually do to the etale hypercohomology of Cn on Xz, because it's certainly not a good definition. There should be another definition of these Weil-Arakelov groups. But it's the picture that we get looks kind of compelling as far as zeta values are concerned. And again, this works for any n. For negative n, people didn't look at motivic homology, but in the etale topology, you can just define the Zns for negative n by push forward from projective space. So the Z minus ones and so on, they would be torsion sheaves, which you can write down just because you know the cohomology of Pn, right? I mean, any n. I mean, because I want to define Z minus n for any n, so I define it inductively from more and more projective spaces, if you like. Yeah, something like that. Yeah. The point is that these strange modifications we do to the etale cohomology, they work uniformly for all n, and so we include negative n as well. Okay, so just like in the finite field case, the key assumption, I mean, motivic cohomology and K-theory are very general. They exist for almost any scheme, but for arithmetic schemes, we have these deep assumptions related to finite generation. I already mentioned them. So the same here. We have to assume that the etale motivic homology is finitely generated in degrees up to 2n plus 1. Same assumption as over finite fields. And then what's new in this context is the Archimedean fibers, and they're related to motivic homology by the Beilinson conjectures, which you can also formulate as a duality theorem. Yeah, so there's a Beilinson regulator map which takes motivic homology tensored with R. So R gamma X Rn is just these groups here tensored with R. Again, my standard Q spaces in the special value conjectures. And then I take the Beilinson regulator map to the Leen cohomology, and I take its fiber, which I call compact support motivic homology. And one can actually construct a pairing between compact support motivic homology and usual motivic homology of this shape. And Beilinson conjectures would be saying that this is a perfect pairing of finite dimensional R vector spaces. Yeah, so while the pairing can be rigorously constructed, also this trace map you can construct. This R is basically the same R that you find as the co-kernel of the Dirichlet unit regulator map. And the hard part is then the finite dimensionality, that this is a perfect pairing again of finite dimensional vector spaces. So Beilinson conjectures are some form of duality. It works then for all n in Z. And unfortunately, it's known only in very few cases, like all of the assumptions that one has in this picture. But it's known for speco F at least. And then my third assumption is much more benign. I have to assume a torsion duality. So once I mod out some integer m from motivic complexes, I'm almost in the usual etale world, except that m need not be invertible on X. Yeah, if m is invertible, then this is usual Poincare duality for etale cohomology. There's no mystery. Combined with Poitou-Tate on speco F, if you like. But m need not be invertible on X, but nonetheless, people have proven this duality in various situations. It's still not known for any regular x, but if x is smooth over spec of f, or if the twist is bigger than the dimension or smaller than 0, even for general regular x, it's proven by Geiser, and so on. Or if I have an arithmetic surface, it's proven for all n. So this is much more benign. It's an assumption that's basically known. And so using this duality, we can actually modify our Weil-etale hypercohomology of the motivic complex into perfect complexes of abelian groups. Oh yeah, this is using Tate cohomology at the infinite prime. That's the hat, yeah, finally there, yeah. So what happens is that on this side, you get non-trivial cohomology infinitely many positive degrees, which is corresponding to infinitely many negative degrees on this. Then, yeah. The Weil-etale regulator? Yeah. I mean, it is just a localization map. You localize motivic cohomology of X to the Archimedean fibers in some sense. But of course, if you define this in terms of K theory, then you have a formalism. What kind of properties a cohomology theory has to satisfy to get a Chern class map from K theory? That goes back to Gillet, I think. And you can verify these properties for Deligne cohomology. So by general construction, you get a Chern class map, which is the Weil-etale regulator. I mean, there would be much more to say. I leave it as a black box, but morally, it's just a localization map from motivic cohomology of X to the Archimedean fibers. Okay, so that's our list of assumptions, and then we can make our modifications. And what do we get? Well, we get Weil-Arakelov cohomology. And the complication is that X is not compact, right? I mean, it is missing the infinite fibers. So instead of just getting a single complex associated to X, we get complexes associated to some Arakelov compactification of X, or Artin-Verdier compactification, whichever way you want to call it. And then we get a mapping fiber, which deserves to be called cohomology of X bar with support in the Archimedean fiber. We get the closed Archimedean fiber X infinity, which is not the same as the fiber over the Archimedean fields. And so we get this whole diagram. Yeah? So this is completely analogous to sheaf theory. If you have a space and an open X in some X bar with closed complement X infinity, you can make the same diagram in sheaf theory, right? So, I mean, you have a restriction map to the open part. The fiber is called cohomology with support in the closed part. You have a restriction map to the closed part. The fiber is called compact support cohomology. Or it's the J-lower Schrieg cohomology of your sheaf. So all of this is modeled on some standard diagram in sheaf theory, but yeah. Yeah, right. I'm not saying what X bar is. I'm just writing down the complexes. It's just. Yeah, in the same way that Arakelov char groups in the end are independent of the choice of metric. You know, there's two variants. If you look at Gili-Sully, there's Arakelov char groups and arithmetic char groups, and Arakelov ones are independent. I mean, the definition depends on it, but in the end, you show they don't depend on it. But what X bar actually is, I leave completely open. We just construct all these complexes by some mapping fiber constructions and so on. Yeah, roughly. So I mean, we have to go a little bit beyond schemes. If you really want to imagine what is the underlying geometric object under this diagram, I mean, X bar won't be a scheme. It will be maybe defined by its category of sheaves somehow, and the same for X infinity. But I mean, this is for future research. I mean, these groups should have a much different definition, but we just construct this diagram of complexes. And where does it live? Okay, so while it's still true that the cohomology of X itself is a perfect complex, I'll give an example in a minute, some other complexes, they only live in the derived category of locally compact abelian groups. For example, look at the lean cohomology. I mean, it's already, it has these complex vector spaces in it. The natural way to view it is as a complex in locally compact abelian groups. You don't want to view C as an abstract group in this case. Yeah, and so that's why we have these more general categories occurring. So you should really view this diagram in dB of LCA. And now, of course, we know by this beautiful condensed mathematics, this embeds fully faithfully in derived category of condensed abelian groups. So you can also view it in there if you like. And so sometimes these complexes are perfect. So this one is always perfect, and if n is less than or equal to 0, all complexes are perfect. So for example, let's take spec F and let's take n equals 0, and then this complex looks like this, where star is just a Q mod Z dual, Pontryagin dual of these finite groups. So I'm mentioning this example because remember, Lichtenbaum had this original idea that you should make a Weil-etale topology replacing Galois groups by Weil groups, which unfortunately doesn't lead very far, but he could reproduce these groups here from this idea. But only after truncation. If you can make a site out of spec F where at each point you replace a Galois group by a Weil group, and then you can compute the Z cohomology of this site, and you get this in low degrees, but it has higher cohomology, so it has some totally infinitely generated higher degree cohomology, which you have to truncate away. So this whole idea doesn't really fly, replacing Galois groups by Weil groups, but at least you get the correct low dimensional groups. So that's what Lichtenbaum did. And then let me give an example. Yeah. No, not of this X, no. Yeah, it's that one, yeah. The X bar has, as we're going to see on the next slide, it has an Arakelov char group in it, which is more like a locally compact group. I mean, we don't want to view this as an abstract group. Oh, yeah, that's coming up. It's coming up slowly. I mean, the point is, unlike over finite fields, the cohomology of X itself is not related to the zeta function. It's the compact support that's related to the zeta function. So these will be related to zeta functions then. Okay, yeah. Yeah, then it's related to X bar, yeah. So this gives the gamma factors and this gives the zeta function, and that's the completed zeta function. Yeah. So I might come to that in one way or another. But let's just see how this diagram looks like in a very basic case, the class number case again. So spec F and n equals 1. So the thing that I claim to be perfect complex looks like this. So it has the units in degree 1 and then pick plus a Z lattice in degree 2, where this Z lattice has the same rank as the units. So my R1 here is the number of infinite places, my R is the number of infinite places, so R minus 1 is the unit rank again. And so such a perfect complex people have looked at in a completely different context. I think going back to Tate in the 1980s, they constructed what's called a Tate sequence, and they got a perfect complex of this shape, even over the Galois group. So you can now imagine a Galois group acting on F, right, some group of symmetries. And then this complex is not only perfect as a complex of abelian groups, but even as ZG modules. And so you get some Galois theoretic invariant out of this complex. And this was the first time this appeared in the literature, and I think people call it a Tate sequence with a ZG action. And so that's what comes out of our formalism for this case. And then the X bar groups, well, you really get the Arakelov char group. You get pick OF bar, which looks like this. So it's the class group times the co-kernel of this unit regulator map. So that's a compact group cross R, right? I mean, you take the unit regulator lies in the sum zero subspace because of the product formula. And so this is compact cross R. And you should really view it as a locally compact group, this pic OF bar. And that's why this lies in the derived category of locally compact groups. So this compact support looks like this. You have two ways to describe it, corresponding to the two exact triangles. So you can either say it's the local units modulo the global units cross the class group, or you could say it's the maximal compact subgroup of the local units modulo roots of unity cross the Arakelov class group. And so the Archimedean triangle here, so it kind of splits, off the motivic cohomology of the local field into its maximal compact subgroup and some stuff that is more mysterious. This would be the cohomology with support in the infinite fibers, but at least it's a direct sum over all infinite points. But you have an R here in degree 2 and a Z in degree 3. Yeah, what else should I say about this? Let me see. If you would make the analogous diagram over a finite field, you would have the Weil-etale cohomology of a point here, right? So this would be ZZ over a finite field. And so here you would have the local field, which would have a valuation map to Z. But here we have an Archimedean local field, so it has valuation maps to R. I mean, absolute value maps to R. So that's why you get an R here instead of a Z somehow. And then this Z here is again, you don't see in usual Deligne cohomology. So this is just Deligne cohomology in this case. It's just this term. But the Weil-Arakelov modification has an extra Z in the next degree. So that's just what comes out of the formalism. And so that's just to give an example what this diagram looks like in the class number case. Okay, now you not only have Zn coefficients, which I was explaining here, you have the same diagram with Rn coefficients, and it's not true that these groups tensored with R are simply the Rn groups. It's true for these when you take the tensor product in the sense of locally compact abelian groups, as introduced by Hoffmann and Spitzweg, but it's not true for all complexes here. So there's a separate construction that constructs this whole diagram with Rn coefficients, and then the mapping cone is the groups with R mod Zn coefficients. So you have this whole collection of groups. So that's what I'm trying to say here. For all entries of my diagram, so that's what I mean by this Y question mark, that covers all entries in my diagram. You have a Zn version, an Rn version, and R mod Z version. And these are exact triangles in the derived category of locally compact abelian groups. And so just to give an example, the H2n x bar Rn would be the real Chow group as defined by Gillet-Soulet. So this comes literally out as this group. And again, it's not the integral Chow group tensored with R. So you have two separate Arakelov modifications for the integral Chow groups and the real Chow groups. And if you took x bar Zn, you would get almost the Arakelov Chow group of Gillet-Soulet without the R here. So it's closely related to Arakelov theory, yeah. Oh, the tilde, yeah, okay. The tilde is supposed to distinguish R with the Euclidean topology from R with the discrete topology. So I told you that Lichtenbaum was trying to make this Weil-etale site out of modules under the Weil group, and then there's a difference if you take R with its Euclidean topology or R with its discrete topology. This is what the continuous, yeah. But it's meaningless. And we define all these complexes by some mapping fiber constructions directly. So we don't take cohomology of some Weil-etale site. So it's a meaningless notation for this talk. Okay, so if you throw in all these assumptions I had at the very beginning, you can prove some very appealing duality theorems. As you would expect, you have a duality between compact support cohomology of X and usual cohomology of X. The top degree is 2D plus 1. So for example, if you have spec OF, it's degree 3. So it's like a 3-manifold duality. You have a self-duality for X bar. So this works out, should be self-dual because it's compact. And yeah. No, because I don't have a site. It's just given by. I mean, this pairing is rigorously defined. The one I had before for the Bailinson, and this is defined by representing all objects in the stable homotopy category and using multiplicative properties of this A1 stable homotopy categories. I can do that because I have everything with Q or R coefficients, and then I can just refer to this formalism, which gives me a multiplicative pairing. It's not really a cup product then. It comes from the multiplicative structure of this stable homotopy category. It is a cup product? Okay. Yeah. Maybe, yeah. Yeah, okay. It's a cup product in the sense that I start with a multiplicative pairing on the coefficients and then I apply sections over X. Yeah. I guess that's right. Yeah. And so I also have Pontryagin dualities. Again, this wouldn't make sense if I just viewed all these groups as discrete groups, right? At least at this point, I really have to talk about locally compact abelian groups. Otherwise, I wouldn't be able to talk about Pontryagin dualities. Here, I can still get away with talking about R linear maps, right? That's a completely algebraic notion to formulate these dualities. But here, I couldn't. So that's another reason to work with this derived category of locally compact groups or condensed groups. So again, these are the expected dualities, and now how is this related to special values? So this is the compact support cohomology that, as I said before, that gives special values, and we do have the versions with Zn, with Rn, with R mod Z coefficients, giving us an exact triangle. And this triangle has the following properties. So the Rn groups are, of course, vector spaces. They're finite dimensional under our assumptions. And we again have this cup theta exact sequence, where now theta is not coming from an H1 class because I don't have a Weil-etale site. I just have a formal construction of this sequence, which is pretty silly, but at least all we do is really just manipulating complexes without a formal. Yeah. Yes, exactly. No. Yeah, okay. I could try to say a little bit more about this, but let's just say at this point that I get the same kind of structure that I had for varieties over finite fields. So that means this complex has vanishing Euler characteristic because I have this exact sequence. And again, typically, it's just concentrated in 2 consecutive degrees. So there's not much going on typically, but that would be the general statement. And so I have vanishing Euler characteristic. That's the property of this group. And then the R mod Z groups, they're all compact. So that means they look like a torus cross a finite group. If you recall this duality here, that's kind of equivalent to saying that these groups are always finitely generated, right? So that's kind of the reflection of this fact I mentioned earlier, that for any n, these groups are finitely generated, so that means by duality, these are always compact. And so, so that's my groups. And again, for the class number formula, that looks like this. So I have my compact support groups, which I already mentioned before. They look like this quotient cross pic in degree 2, a Z in degree 3. This maps to an R in degree 2 and 3. So here I have the obvious map, and here I have the absolute value map on the local field. So this is sort of log absolute value. I mean, here I have mentioned my map. So that's this map. From this F R cross to this R is this map. So the kernel of this map modulo units is compact. Of course, pick is finite, so this whole group is compact, and R mod Z is compact, and so I verified my compactness for these groups here. So this is the R mod Z cohomology. And I not only get compact groups, I even get a measure on these compact groups, namely by the exponential map. I need to find a measure on the additive group, and I take the measure that normalizes the volume of the units to 1. So my unit lattice in the additive, it's just the additive OF lattice normalizes the volume on this tangent space. So this would be, if somebody remembers still my discussion of the Bloch-Kato-Tamagawa number conjecture, there was always this tangent space of a motive. So this would be the tangent space, and I have an integral structure in this tangent space which normalizes the volume. And so you can more or less see the terms in the class number formula coming out. I mean, they're all there in the volume of these compact groups. This you don't see because it has sort of volume 1. Okay, so then the general statement as far as the relation to zeta function is concerned, again, just like over finite fields, the vanishing order is given by the secondary Euler characteristic, and the leading Taylor coefficient is given by the volume of these compact groups. I could have stated the same statement in the finite field case. I just didn't talk about the volume of the cofiber from Zn to Rn coefficients, but the statement I had using this chi with respect to cup theta is equivalent to a volume statement for the compact R mod Z coefficient groups. Do we have to stop? I think I'm way behind. Okay, so that's the picture. So because X is not compact, the zeta function is really related to compact support motivic homology. And the vanishing order is given by secondary Euler characteristic, and the leading coefficient is given by this volume. Now what I have to explain to you at this point is what is the normalization of the volume in this general case, right? I mean, I told you these groups are always compact, but that doesn't mean I have the canonical volume form. So I have to tell you what is the analog of this OF, the natural lattice in the tangent space, that normalizes the volume correctly. And since it's almost time to end, I'll do that next time. So let's just finish by, oh, that's already here. Okay, so, yeah. So that's a longer story, so I'll start with that next time. Maybe it's time to stop here, and then just tell everybody that you can easily work out the class number formula from this picture here. I mean, that would be the final exercise for this lecture. Okay, let me stop here. Yeah. Yeah, I mean, it should actually work very generally whenever you have an open-closed decomposition of a scheme, for example, the special fiber and some open complement. I mean, zeta functions, they're always multiplicative for open-closed decompositions, right? Because you just count closed points. And then whatever cohomological formalism you have to describe zeta functions should be similarly, you should have an exact triangle for an open-closed decomposition, which is what you have for compact support cohomology. If you think of the usual alatic theory, you have such a triangle. And yes, so there is a connection then between the open and the closed part by this triangle. And it works completely over finite fields. So over finite fields, you can take any X, not necessarily smooth proper, and you have these Weil-etale groups that was worked out by Geisser. And we expect that to be true over number fields as well, but I want to restrict myself to proper regular situation just to make things simpler for this talk. And the finite field, yeah. I mean, if you, um, I mean, you would have a localization triangle for the mod P fiber with X and its open complement, yeah. And then each one has a zeta function, and the finite field picture is compatible with this. Yes. Yeah. Oh, was that the question? Yeah. I mean, you could do that. It would mean that your whole diagram, this collapses. This is all zeros, and or maybe in more generality, uh, this is all zeros over a finite field, and these groups all coincide with the Weil-etale groups I had previously. And yeah, you could work it out over finite field. And also the way we define these groups using duality instead of some Weil-etale topos, you could also make over finite fields. So in this sense, it's uniform. It works for finite fields. Yeah. Um, I don't think I'll get exactly Chow groups that these authors consider, because I think they look at higher arithmetic Chow groups or something, which okay, yeah. Um, I mean, there are certainly connections. I mean, um, people often look at the mapping fiber of this, but sometimes they don't tensor the mapping. They don't tensor here with R, so you get different groups. Yeah, so you have to look exactly what's done in those papers, and then there would probably be some connection. But I don't think we literally get the same groups necessarily. Yeah, yeah. It's just a mapping fiber of the Beilinson regulator map. That's all. So um, s- so here I have usual motivic cohomology tensored with R. Yeah, so I really make this an R vector space, and that's the mapping fiber. That's all. Um, yeah. No, but then I need the X bar thing. Yeah, yeah. So I need these. Um, so if you take the X bar with Rn coefficients, it describes the vanishing order of the completed zeta function. Yeah, and this with Rn coefficients gives the gamma factors. Um, but over finite fields, yes. It has, for the X bar, it has the same behavior in that it only lives in degree 2n and 2n plus 1, just like over finite field. Yeah. So you just have the usual Chow groups. The higher Chow groups are torsional. They don't have a rank, just like over finite fields. Yeah, that's right.